Hi, Reddy Satyanarayana. Welcome to this chemistry class. So, hello students. Good evening to all of you. So, am I visible and audible to all of you? Can you just let me know in the chat box if I'm visible and audible? If I'm visible and audible. Yes? Okay, Madhupriya. So I have started D and F block lessons. Yes. Thank you, Reddy. And so I was discussing about the D and F block lessons on last Friday, and today I am going to continue with that lesson. So in last class, I have discussed the position and electronic configuration with you all, and the general properties. And under general properties, I have discussed the physical properties. Just a second. Sorry for the interruption. Just a second. So can you see my screen? Can you see my screen? Is my screen visible? Just put it in the chat box if my screen is visible now to both of you. Yes. So who are the two here? Madhumita and Reddy, right? So Reddy, Madhupriya, yes, Madhupriya and Reddy Satyanarayana, just put it in the chat box if my screen is visible to both of you. Just type yes if it is visible, or type no if it is not visible. Okay. Okay, dear students. Thank you so much. Thank you. Yes. So in the last class, as I have told, that I was discussing the position and electronic configuration of the D block elements, which are called as transition elements. And I have categorized this general properties into 3. And under this 3, I was discussing about the part 1 properties, that is the physical properties and ionic size and ionization energy. These 3 properties were discussed on Friday. Okay. And today I am going to start with the oxidation state. So coming to the physical properties of transition metals, they are the good conductors of heat and electricity, and they are ductile, they are malleable, and what else? They have ionization energy also. Ionization energy is increases on removing the electron, and for half-filled and completely filled system, ionization energy is very, very high since they are very stable. Okay, these things were discussed. And today, coming to the oxidation state of this transition elements. So let me start with the D series. And only D series oxidation states are mostly discussed here in this lesson. And 4D, 5D series will also be discussed. Okay. There are 4 D series. One is 3D, the other one is 4D, 5D, and 6D. So the 3D series starts from scandium and ends on zinc. From scandium till zinc, you have to know the atomic number and you have to know the electronic configurations. Okay. Without knowing these two, the oxidation state topic will be difficult for you. Got it? So scandium till zinc, you have to study atomic number and electronic configuration. Got it? And coming to the oxidation state here, you can see that scandium is having only one oxidation state, which is +3. And zinc is also having only one oxidation state, which is +2. And the remaining elements, they are having from 2 till 6 oxidations. 2 in case of copper and 6 in case of manganese, you can see. So what is the general statement we can give for this D block elements? D block elements are able to exhibit variable oxidation states. D block elements are able to exhibit variable oxidation states. Okay. So if you see the P block and S block elements, they can exhibit only one oxidation state. One element can exist only in one oxidized form. But in case of D block, they have multiple oxidation states. That is their specialty. Okay. And you can see some yellow color numbers here. Some numbers are in yellow. So those yellow states represents the most stable oxidation state of that particular element. For example, in case of nickel, you see +2 is the most stable state of nickel. So nickel can exist or it is stable only in +2 form. Okay, most stable states are given, and +2 state is the most stable state for most of the elements you can see. From manganese till zinc, +2 is the most common oxidation state for those elements. Okay. And yeah, for scandium and zinc, it is only one oxidation state. So the scandium electronic configuration is 3D1. It is 3D1 actually, 3D1 and 4s2. 3D1 and 4s2. So if all the 3 electrons, it is 3D1 and 4s2, right? So if all the 3 electrons are removed from the scandium, I'll get scandium 3+ as the configuration. And if all the 3 electrons are removed, this scandium will have 0 electrons in its 3D orbital, right? So because of that particular purpose, +3 oxidation state is the most stable oxidation state for scandium. Okay. So then coming to zinc, it is 3D10 and 4s2. 3D10 and 4s2. So if I am going to remove 2 electrons from this s orbital, then I would end up with zinc 2+, right? Why zinc 2+ is more stable? Because it is having 3D10 configuration, which is fully filled, which you can see here. So D0, D5 and D10 configurations are more stable. Okay. And that's why that particular oxidation state of that element is stable. Zinc 2+ and scandium 3+. Okay. And coming to copper. So students, if you're having any doubt here in this slide, you can ask me. Only two elements exist in only one oxidation state, that is scandium, and the other one is zinc. Zinc is not the transition element, but it is the D block element. Okay. Zinc is not the transition element, but it is a D block element. Transition element definition we have studied. So either in the neutral form or in one of its oxidized form, the element should have incompletely desorption. Then only it is called as transition element. Here you can see in case of zinc, its oxidized form is zinc 2 plus. Its neutral form is zinc. In both the cases, it is having this D10 configuration. D orbital is completely filled. It is not incomplete in both the cases. So that's why it is not regarded as the transition element. But it is a D block element because the last electron enters into the D orbital. That's why it is called as D block element. So the only transition element which has only one oxidation state is scandium. Okay, scandium is the only transition element which exists in only one oxidized form, which is +3. Got it? So students, if you're having any doubt, you can raise your hand or you can put it in the chat box. If there are no doubt, just type yes in the chat box. I'll go for the next slide. If everything is clear to you, you can just type yes in the chat box so that I can understand that you have understood. And I'll go for the next concept. Shall I go? Shall I go with the copper? Shall I go with the copper story? Okay, I'll go with the copper. So copper has +1 state as well as +2 state. +2 state, as I have told you, it is the most common oxidation state for most of the elements. And the early transition elements. Which one you want me to repeat, my dear? This slide, copper story, or the previous slide? Previous slide. This one you want me to repeat? Yeah. See, D block elements have variable oxidation state. That is the first point. D block elements have various oxidation state, and scandium is the only transition element which has +3 oxidation state, only one oxidized form. And zinc is also having only one oxidation state, but zinc is not the transition element. Why it is not called as transition element? There are no incomplete subshells in it. Only if a compound has incomplete d orbitals, it is called as transition element. Since zinc has fully filled the d orbital, it is not called as transition element. It is the D block element. Clear? Clear? Hi Pratibha, good evening. Satyanarayana, is that clear? Yes. So now coming to the story which I was discussing, copper is the only element. Yes, copper is the only element which has +1 oxidation state. Only that exists in +1 state. The remaining elements you see, they are not existing in +1. Only this copper exists in +1. Yes, good evening, good evening. The early transition elements, that is from scandium till manganese, the first 5 elements, which are otherwise called as early transition elements, they are existing in their highest oxidation state. They are existing in their highest oxidation state. But from moving from iron to zinc, you can see the irregularity. That is, for iron, even though we have 8 electrons in its outermost shell, +8 is not the highest oxidation number for iron, right? So plus 6 is the highest oxidation state. So suppose in case of scandium, the electronic configuration is 3d1 and 4s2. Since scandium has 3 electrons as the valence electron, it is existing in plus 3. Highest oxidation state is plus 3. Now coming to titanium, titanium's electronic configuration is 3d2, 4s2, right? So how many electrons we have? We have 4 electrons in titanium. So plus 4 is the highest oxidation state for titanium. And coming to vanadium, the electronic configuration of vanadium is 3d3 and 4s2. So totally we have 5 electrons. So the number of valence electrons is equal to the highest oxidation state, which is plus 5 in case of vanadium. And the same way for chromium also, the electronic configuration is 3d5 and 4s1. So the total electrons are plus 6. So that is the highest oxidation state. And coming to manganese, the configuration is 3d5 and 4s2, which is 7 here in this case. The 7 here in this case, and that is the highest oxidation state. Okay. But coming to this iron, what is our configuration of iron? It is 3d6 and 4s2, right? How many electrons are there for iron? It is 8. So the highest oxidation state for iron is not 8. It is just 6. So the total number of valence electrons is equal to the highest oxidation state concept is applicable only for the early transition elements. It is applicable only for early transition elements, and it is not applicable for post-transition elements. It is not applicable for post-transition elements. Got it? So iron is not having plus 8. Got it? Just a second. Yes, students. Students, is the concept clear for all of you? Shall I go with the next thing? Now coming to the next part. So this oxidation state depends on the 3 things. One is empty configuration, which is D0. The other one is half filled. It is actually half filled. It is not D6. It is D5. D5 configuration and D10 configurations. So the stability of D10 is more compared to D5 and D0. Suppose in case of titanium 4 plus and titanium 3 plus, which is more stable? Titanium 4 plus is more stable. Why titanium 4 plus is more stable? Because the titanium electronic configuration is 3d2 and 4s2, right? So 4 electrons are there. If it loses its 4 electrons, it would have titanium 4 plus, which is 3d0 configuration. Titanium 3 plus means you have to remove only 3 electrons. It is 3d1. So D0 is more stable than D1. That's why titanium 4 plus is more stable than titanium 2 plus. Got it? Now coming to manganese 2 plus and manganese 4 plus. The configuration of manganese is 3d5 and 4s2. Okay. So how many electrons? 7 electrons are there, and if 2 of its 4s electrons gets lost, then manganese will have 2 plus state by having 3d5 electrons and 4 is 0 electron. So 3d5 is half filled. And how many electrons would be there in case of manganese 4 plus? You have to remove 4 electrons from this. On removing 4 electrons from this, we would have only 3d3 and 4 is 0. So you see 3d3 and this is 3d5. 3d3 is partially filled configuration and the 3d5 is half filled configuration. Which is more stable? Half filled configuration is more stable. Half filled configuration is more stable compared to partially filled. That's why Mn2 plus is more stable than Mn4 plus. Okay? Clear? So coming to the periodic table, as I have told you, the S block elements exist only in one oxidation state. That is group 1. For group 1, it is +1, and for group 2, it is +2. Now coming for P block elements, it also exists in only one oxidation state. That is +3 for group 13, +4 for group 14, and etc. Okay. That thallium, lead, and bismuth, these three elements are having only +1, +2, +3 states. In case of 13th group, all the 13th group elements exist in +3 state except thallium. Means thallium will exist only in +1 state. So likewise, all the group 14 elements will exist in +4 state except lead. Lead will exhibit only +2. The same way, all the group 15 elements can have +5 state except bismuth. Bismuth can exist only in +3 state. Got it? These are the exceptions found in P block. Now coming to D block. D block elements are able to exhibit variable oxidation states. There is no such specific oxidation state for group 3 till group 12. Got it? So this is about the oxidation state of D block. And some of the highest oxidation state containing compounds are shown to you on the screen. Manganese, the highest oxidation state for manganese is +7, and the +7 is existing in KMnO4. What is KMnO4? KMnO4 is potassium permanganate, right? You can see the oxidation state of manganese is +7. So for potassium, it is +1, and I'm going to calculate for manganese, so I'm taking it as X. And for each oxygen, we have to give -2. So 4 into -2 is -8. So equal to 0. So what is X? 8 minus 1, it is equal to +7. So the oxidation state of manganese is +7, right? And in case of this ruthenium tetraoxide, you see, ruthenium is taken as X. And for each oxygen, -2. So 4 into -2, -8, equal to 0. So X is equal to +8. So that is the case. The same case in with osmium also. So the highest oxidation state for D block elements are +7 and +8, and those states are existing in these compounds. Got it? Clear? Then coming to, yeah, this is the most stable state, and coming to the zero oxidation state containing compounds. Zero oxidation state. You know, all the tetra, penta, hexa, all the carbonyl containing compounds are having zero oxidation state, because this carbonyl is a neutral ligand, neutral component. So if I am taking this nickel as X, I will put 0 here, which is equal to 0. So X is equal to 0, no? So all the CO containing carbon monoxide, which is called as carbonyl, all the carbonyl compounds are neutral in nature. Means the D block elements which are bonded with carbonyl will have zero oxidation state. Got it? See the structure. Nickel tetracarbonyl. This is C and this is O in each case. So nickel tetracarbonyl is having tetrahedral structure. This is your tetrahedral structure, and this is your iron pentacarbonyl is having trigonal bipyramidal structure. Iron pentacarbonyl is having trigonal bipyramidal. So 3 CO will be on the plane, and one is above and the other one is below. So it is trigonal bipyramidal. Got it? If you connect all the trigonal planar atoms to this particular carbonyl, you will have one pyramid above and another pyramid below. Trigonal bipyramidal geometry. Okay. So next I'll go for one more concept regarding the oxidation state. If the oxidation state increases, ionic character decreases and the acidic character increases. Okay. If the oxidation state increases, ionic character decreases. Or otherwise, how can I say this? Covalent character increases. Covalent character increases and acidic character also increases. Got it? So you see this. So I have given 3 compounds to you on the screen. And the oxidation state of manganese in each compound is given here. If the oxidation state increases, acidic character is more. Right? So Mn2O7 is having the highest oxidation state. Means that is more acidic in nature. And its ionic character is very less. So covalent character is more. That's why the compound is covalent in nature. Got it? So what is the concept? On increasing the oxidation state, the ionic character decreases and acidic nature increases. So the +4 manganese compound is amphoteric, +2 manganese compound is basic, +7 is acidic. What is amphoteric? What is amphoteric? The one which can act as a base as well as an acid. That's why it is called as amphoteric. Okay. Clear, students? Yes. Now coming to the next part. The next concept is the oxidation state of chromium group elements. For chromium group elements, that is chromium, molybdenum and tungsten, only molybdenum and tungsten exist in their highest oxidation state, which is +6. So what is the electronic configuration for this chromium group elements? It is 3d5 and 4s1 for chromium. And for molybdenum, it is 4d5 and 5s1. And for tungsten, it is 5d5 and 6s1, right? These are the electronic configurations. And in all the cases, you can see there are 6 electrons in their valence shell. So +6 is the most stable highest oxidation state for that particular group. But only molybdenum and tungsten exist in +6 oxidation state in these 2 compounds. Okay. Chromium will not exist in +6 oxidation state. So what is the concept from this particular thing? Stability of higher oxidation state increases on moving down the group. You take down the statement. All of you write the statement. Stability of the higher oxidation state increases on moving down the group. Okay. So this is the concept. So on moving down the group, only the +6 is more stable. Tungsten is stable in +6, whereas chromium is unstable in +6. Okay. So you just see chromium doesn't exist in +6. It exists only in +3 form. That's why it is acting as an oxidizing agent. What are oxidizing agents? Electron acceptors, right? Electron acceptors are called as oxidizing agent. So chromium is an oxidizing agent. Coming to the next property, which is standard electrode potential. So students, I just want to ask you a question. So do you have any doubts here in this oxidation state property? From the topics, from the concepts which I have discussed under oxidation state property, general property. So what is the first point? Under this oxidation state, they exhibit variable oxidation state, and D0, D5, D10 configurations are more stable. Okay. And what is next? The higher oxidation state becomes more stable on moving down the group. This is the concept which we have studied at last. And when oxidation state increases, the compound is more acidic in nature, and the ionic character decreases for that particular compound. Okay. So these are the topics, very important points which we have discussed here in this oxidation state. Now coming to the next physical general property, which is standard electrode potential. Standard electrode potential for you. So you can see the standard electrode potential graph for metal 2+2 metal couple. So in this x-axis is occupied by our 3D series elements and y-axis is our standard electrode potential value, right? And this is the axis and this is the negative side and this is your positive side. So all the elements are having negative electrode potential except copper. Except copper. So only copper is having the positive electrode potential value. Okay. So if an element is having the negative electrode potential value, then only that particular element can act as a reducing agent. The elements which are having negative electrode potential can act as a good reducing agent. Since copper is having positive electrode potential, it is not a good reducing agent at all. So what is the role of reducing agent? It will go and donate its electron. So all these elements except copper, they can donate their electron easily. In case of manganese, manganese can donate its electron. It can lose its 2 electron easily. Iron can lose its electron easily. Cobalt can lose its electron easily. But copper, it will not lose its electron easily. Okay. So it is not a good reducing agent. Yeah, it is having positive electrode potential value. The copper will not lose electron easily. Rather, it will gain electron easily. Okay. It has to lose electron, no? But since it is having positive potential value, it is gaining the electron. It is gaining 2 electrons and turning into copper 0. And also it doesn't react with hydrochloric acid. It does not react with the hydrochloric acid. Why it doesn't react with the hydrochloric acid? Hydrochloric acid is not a strong oxidizing agent. Okay, it is not a strong oxidizing agent. But other metals from titanium till zinc, they are reacting with the HCl and forming a salt and hydrogen gases evolved. Okay, copper is less reactive. Copper is less reactive, so it cannot displace the hydrogen. Copper cannot displace the hydrogen since copper is less reactive. Okay, that is the main reason. So hydrogen gas is evolved in case of other metals with the HX. So other metals are the good reducing agents, while copper is not the good reducing agent. Copper doesn't react with HCl, but it is reacting with H2SO4 and HNO3. It doesn't react with hydrochloric acid, since hydrochloric acid is not the oxidizing agent. But it is reacting with sulfuric acid and nitric acid because they are oxidizing agents. They are the strong oxidizing agents. So that's why they are oxidizing this copper 0 to copper 2+. So copper reacts only with sulfuric and nitric acids with the evolution of H2. And it doesn't react in case of HCl because HCl is not an oxidizing agent. Got it? Clear, students? If you have any doubt, you can put it in the chat box. Okay. Now coming to some informations. You can see a tabular column on the screen for all the 3D series elements. The first column is the atomization. Enthalpy of atomization values are given. And this is the first ionization energy and second ionization energy. And the hydration enthalpy is given to you on the fourth column. And the standard electrode potential value is given in the fifth column. Okay. Now, across the period from titanium till zinc, manganese, nickel, and zinc. Manganese, nickel, and zinc. These three are having the highest, these three are having the very less second ionization energy value. These three are having the very less second ionization energy value. In case of manganese, you see the ionization energy of manganese is 1509. But here you see it is 1592. If it is 1592, here it should be something around 1600. No, but it is decreasing. Actually, it should increase. It is increasing from titanium till chromium, but suddenly it is decreasing to manganese. Why decreasing? Why second ionization energy is decreasing? Because on removing the second electron, which is present there in 4s, if I am removing this electron, I am getting D5 configuration for manganese, which is more stable, since Mn2 plus leads to a more stable configuration, or since the removal of second electron leads to the more stable configuration, we can remove that particular electron so easily. That's why the energy required to remove that particular electron, which is called as ionization energy, is very, very less. Got it? By removing an electron, if a system attains the more stable configuration, then only very less amount is needed. Less amount of energy is needed, or it is enough to remove that electron. That's why the energy value decreases from chromium to manganese. And coming to zinc, till copper it is increasing again. And suddenly for zinc, from 1900 it is decreasing to 1700. Why? On removing the second electron, zinc attains zinc 2 plus configuration, which is more stable because of fully filled. And that's why it is very easy to remove the electron, so the energy value is less. Clear? Energy value is very less. You can easily remove that second electron. That's why it is less. And coming to nickel, nickel is related with high negative hydration energy. So this is the hydration energy column. And here you see it is hydration energy is for decreasing, then increasing, then decreasing, increasing. And suddenly nickel and copper, they are having the same hydration energy value. Actually, for nickel, the value should be around 2000 only. But it is having 2100. Why? Why it is having the high negative hydration energy? Because its charge to radius ratio is very, very less. That is, the size of the nickel ion, nickel 2 plus ion is very small. The size of the nickel 2 plus ion is very, very small. So hydration energy for small size cation will be more negative. What is hydration energy? When you put a salt into the water, the H2O molecules which are there in the water, they will come and form the bond with the cations and anions. That is the negative part, partially negative part of the water molecule, which is oxygen. It will come and form the bond with nickel. Okay, likewise from all the sides, nickel will form the bond with oxygen. Okay, so here what happens? Here bond formation is occurring between oxygen of water molecule and the nickel of the nickel 2 plus from the salt. So here bond formation occurs, and whenever a bond forms, energy will be released. Okay, energy will be released. Since energy is getting released, we have to represent it in terms of by putting negative, by putting minus in front of it. Yes, Pratibha, tell me. Pratibha, you have raised your hand just. Yeah, tell me. You have any doubt here? If you have any doubt, just put it in the chat box. Pratibha, you have doubt? No? Or just by mistake you have raised your hand? Huh? Okay, no issues. Okay, I'll continue with the class. Listen carefully. So here, a bond is being formed between nickel 2 plus and oxygen. So during bond formation, energy is released. So that's why the hydration energies are given with the negative sign in front of it. Okay. So if the size of the cation is very, very small, then that particular system will have more negative hydration enthalpy value. Since nickel 2 plus size is very small, as its charge to radius ratio is very less, it is having the very high hydration enthalpy value. Got it? High negative value. Yes. So I'll go with the next topic. The stability of higher oxidation state. So you can look into the tabular column and you can see that for all the compounds which are given here are the halides. Okay. All our 3D series are bonded with halogens, fluorine, chlorine, bromine and iodine. And here you can see titanium, vanadium and chromium. They are existing in their very high oxidation state. And for titanium, it is +4, no? For vanadium, the highest oxidation state is +5. And for chromium, it is +6. So these three elements are forming the strong bond with fluorine and they are existing in their highest oxidation state. But yeah, why they are having highest existing, why they are stable in highest oxidation state? Because of their high bond energy. Because of their high bond energy. So if let me take this chromium. Okay. So if this is chromium, this is your CrF6 compound, right? So since fluorine is very small in size, the bond, this bond between chromium and fluorine, it will be very strong. So if you want to break this bond, you have to supply more energy, right? So high bond enthalpy. Bond enthalpy is nothing but bond energy. Since the breaking of CrF bond requires the high bond enthalpy, we cannot break the bond so easily. We have to supply more amount of energy to break the bond. Got it? So that's why that particular molecule is more stable. The bonds will not get broken down so easily. That's why they are stable. But in case of manganese and iron, you see, manganese is having +7 oxidation state as its highest oxidation state. But with the fluorine, no. But with the fluorine, it can form only +4. But with the fluorine, it can form only +4. KMnO4, in KMnO4 compound, it can exhibit +7. In MnO3F, it is exhibiting a +7. But with the fluorine, with the halides, it cannot form +7. The highest is +4 only. Hi, Shrikruti. Good evening. Coming to iron and cobalt, if you see, iron is having 3+. Iron is having 3+ as the highest oxidation state and cobalt is having a 3+ state. Even they are not exhibiting their highest oxidation state. So only titanium, vanadium and chromium, they exist in their highest oxidation state. Got it? So this is about the stability of higher oxidation state of various compounds. And coming to the next part, copper story. Copper is having +1 oxidation. Copper is the only element which exists in +1 oxidation state, but in the lower oxidation state, it cannot form fluoride. You see, it is X3, right? X3 means it is from chlorine till iodine. So copper can have CuCl, it can have CuBr, it can have CuI, but it will not form CuF. It will not form CuF. It cannot form fluoride. CuF is not possible. Then coming to +2 oxidation state of copper. With fluorine, chlorine, bromine, it is forming. But with iodine, it is not forming. So copper +1 is stable only with chlorine, bromine, iodine. The copper 2+ is stable only with fluorine, chlorine, mostly. Even bromine will not form this. It will not form so easily. Okay. Only fluorine and chlorine can form the bond. Got it? So This is about the halides. And coming to the oxides of all these groups. You can see some of the oxides, not some of the oxides. These are the possible oxides formed by the 3D series. And from early transition elements from scandium to manganese, they are having their highest oxidation state containing oxides, as they are having their valence electrons from +3 till +7. But iron, you see, from iron, cobalt, and nickel, there is no regularity. Iron is having +8. Iron is having 8 electrons in its outer shell, but it cannot form oxide with the +8 state. It can form only with +3, okay, in Fe2O3. And it decreases. Oxidation state also decreases for post-transition oxides. Now coming to oxide and fluoride of 3D series. Oxides of the 3D series are more stable in their highest oxidation state compared to fluorides. You can see an example on the screen. So manganese is having +7 state when it is bonded with oxygen, but it is having only +4 state when it is bonded with fluorine. Okay. So when they are in their oxide form, the highest oxidation state for that particular element is more stable compared to fluorine. Okay. So any doubt so far? Any doubt so far? Both of you? If you have any doubt, just put it in the chat box. Pratibha and Shrikruti. So I have discussed about the oxidation state of oxides and the fluorides with the both of you. So you have any doubt? See, if you understand the concept, it is going to be easy only. Just understand it. Just read again and again. Read it consistently. Everything is going to be easy for you. You can clear so easily if you're getting questions from D and F block, proper test topic. Okay. If you're having any doubt, you can ask me. Shall I continue with the next property? So oxidation state and electrode potential properties got over. Shall I proceed with the next property, which is called as magnetic property? Yes. Just type yes in the chat box. If I can move. Magnetic properties are, they are very easy questions will be asked from that. So I'll move on to that. So you can see a GIF. What is that? A person is bringing a magnet towards a substance, and that substance is getting attracted to that magnet. Okay. So what is that substance? Let me take that substance as a D block element. Okay. It is getting attracted to the magnet. So the magnetic behavior of an element can be studied under 3 topics. An element or substance can be diamagnetic, or it can be paramagnetic, or it can be ferromagnetic. Okay. So what are diamagnetic substances? Yeah, before moving on to this, I'll tell you what is diamagnetic substances. Substances which are repelled. Substances which are repelled in presence of the magnetic field are called as diamagnetic. And what are paramagnetic? Paramagnetic are the substances which are attracted, which are getting attracted to the magnetic field. They are called as paramagnetic. And what is ferro? Substances which are attracted very strongly to the magnetic field are called as ferromagnetic. Okay. Now, how to find out whether a particular D block element is paramagnetic or not? Okay. You can find this by seeing their unpaired electron. Unpaired electron is directly proportional to the paramagnetic property. Okay. So if the number of unpaired electron is more, then paramagnetism is more. You see here, in case of chromium, we have 3d5 4s1 configuration for chromium, which has 6 unpaired electrons okay, which has 6 unpaired electron. So it is paramagnetic in nature. And in manganese, you see 3d5 and 4s2. 3d has 5 unpaired electron. So it is paramagnetic in nature. And in case of zinc, you see, zinc is having 3d10 configuration. Zinc is having 3d10 4s2 configuration. No unpaired electrons are there. All the electrons are paired. So it is diamagnetic. If all the electrons are paired, then the system is diamagnetic in nature. It will get repelled in presence of the magnetic field. If a substance is having unpaired electron, it is paramagnetic in nature, means the substances will get attracted towards the magnet. Okay. Now, yeah, this is the relation which I have told you. Unpaired electron increases, paramagnetism also increases. Now, coming to the electron and its movement, electron can rotate about its own axis and it can rotate the nucleus also. So like our earth is rotating, it is rotating around its own axis as well also it is rotating the earth, no? Sorry, rotating about the sun, no? So likewise, this electron is considered as a planet which is rotating around its own axis and also it is rotating the nucleus. So because of this movement of electron, there is a magnetic moment associated with it. And that magnetic moment is represented by the symbol mu. There is a formula to calculate the mu, which is root of n into n plus 2, where n is the number of unpaired electron and the unit of dipole moment is magnetic moment is Bohr magneton. Okay. So just by using this formula, we are going to solve questions in our NEET exam and JEE exam. Okay. So you can see various ions having colors. So this is the next property that I'll teach you in the next class. So I just want to ask you one question from this magnetic property. So can you calculate the magnetic moment for chromium 2 plus? Can you calculate the magnetic moment for chromium 2 plus? Okay, I'll discuss. So what is the electronic configuration for chromium? It is 3d5 and 4s1, right? Suppose if chromium is existing in 2 plus form, we have to remove 2 electrons. One from 4s and one from this 3d goes out. So we have 3d4 and 4s here. Now put these electrons in d orbitals. So 1, 2, 3, 4. So d orbital, 3d orbital contains 4 electrons. So what is the n value? N value is 4. Now substitute this n value here in this mu. Mu is equal to root of 4 into 4 plus 2. So 4 plus 2 is 6. 6 4 is 24. So the answer is root 24. Answer is root 24. Like around 4.90 Bohr magneton you will get. Okay. Clear for all? Clear for both of you? Like this only you are going to find out. You can ask me, ma'am, how can I know the value of root 24 and all? So if the root value, if the number of unpaired electron is 1, then the mu value will be 1 point something. 1.414 you will have. And if the number of unpaired electron is 2, then the mu value is 2.73. And if the number of unpaired electron is 3, then the mu value will be around 3 point something. If it is 4, it is 4.9. If it is 5, it is 5.92. Okay. So the number of electrons are denoted by the first number here in the dipole moment or magnetic moment values. Got it? Just you memorize these and get the answer. If they are asking you in terms of decimals, you can go through this. Got it? Clear for all? So the next property, the formation of colored ions property, I will teach you in the next class. Got it? So any doubt for both of you? You have any doubts? If you have any doubt, just put it in the chat box. Just put it in the chat box if you're having any doubt. No doubt? Okay then. So I'll meet you tomorrow at 4 p.m. Thank you, students. Thank you so much for listening the class. Go and study. Go and study the same lesson in your book. And from your workbook, you solve some questions also related to this particular topic which I have discussed, from oxidation state, from standard electrode potential, and from magnetic property. From these three topics, you study the concept and solve the question. Okay. Okay then. Thank you. Thank you so much. Thank you.